So now that we're done looking at the implementation of the prototype pattern in C++, let's go ahead and take a look at some other things to consider when you decide to apply this pattern or when you want to apply this pattern most effectively. So we'll start with some of the benefits. It makes your code more flexible. You can add and remove new prototypes at runtime by simply cloning them as you need them, much like stormtroopers in the Clone Wars from Star Wars. You can clone them infinitely and get more and more of them. Not sure that's necessarily the best thing, but things turned out well in the Star Wars movies in the end, so it wasn't so bad. Another consequence is less coupling. By using this pattern, it reduces or minimizes the need for lexical dependencies that bleed through the code at runtime. So if you take a look here, for example, you can see that the bridge patterns abstraction class, which is the expression tree operator plus post increment variant, has no lexical dependencies on the concrete type of the iterator implementation that it's encapsulating. So if you look down below, the clone method knows the specifics of what it's making a copy of, but that is not exposed to the portion that actually requires its use in the abstraction role of the bridge pattern. There are some downsides, of course. There's potentially more overhead because in order to be able to clone something, you have to have instantiated it in order to clone it. So that means it already has to be created before you can make a copy, which is a little different from, say, the factory method pattern or abstract factory pattern. This turns out not really to be a big deal for our expression tree processing app use case because we already had the iterator impl created already, and now we're just using its clone facility to make a copy of it. And there's also some tricky issues with tight coupling. So if you have classes that have circular dependencies on each other or circular references, then you really can't clone them because where do you start? It's like a Mobius strip. No matter where you start, you end up back in someplace else. And another issue would be, of course, if you have classes that don't allow themselves to be copied. And there are lots of those classes. A good example is the C++ unique pointer class that's part of the standard library. It defines the copy constructor and the assignment operator as deleted. So you can't actually make a copy of a unique pointer. So obviously you couldn't clone that. There's a number of implementation considerations that the Gang of Four book talks about. One of them is how do you manage all the prototypes in your program? And one time-honored way to do this is to make some kind of prototype manager, which is typically implemented as an associative container like a map of some kind or a multi-map where you have key value pairs, and you can use those to amortize the creation and destruction or consolidate the creation and destruction of the prototypes by putting them into a map and then looking them up by their key. And that way you could pre-allocate them, you could reuse them, you could share them. There's all kinds of benefits that come from using some kind of map-based manager. Another interesting consideration to think about is, do you need to make shallow copies or deep copies? And these are often issues with programming in general, and that's in fact why C++ defines copy constructors and assignment operators to take better control over shallow copies versus deep copies. One of the things you can do is use a shallow copy where the copy only copies the top level object but doesn't copy any of its inner nested objects. Those remain shared between the original object and the clone object. So the referenced object is therefore shared. So any change to the underlying referenced object will have the side effect of affecting both the original object and the cloned object. So that's what's typically called a shallow copy. There's also something called a deep copy, which will make a fully independent copy of the object and any of its internal or inner nested objects or sub-objects. And so, of course, what happens in that case is any changes to the reference object will only affect the object that it's been cloned by with a deep clone or a deep copy, not any other copy that's been deep cloned or deep copied. So it all depends on really whether you want those things to be shared or not. There's a whole bunch of known uses. There's some interesting known uses described in the Gang of Four book going way back to something called ThingLab, which I think was Evan Sutherland's PhD dissertation back in the 60s. And so just goes to show that these patterns have been around for a long time. Jim Copleen's classic early book on patterns and styles and idioms for C++, which was many people consider to be sort of the precursor to the patterns movement that appeared in the early 90s, also describes the prototype pattern in terms of C++ idioms. and gives a whole bunch of examples and variations of this type of an approach. So it's been around and known in the C++ community for a long time. And of course, I would be remiss to not mention the java.lang.object clone method, which is precisely defined to use as part of the prototype pattern. There's pros and cons of using clone. Clone was very popular when Java first came out. I think it's kind of been deprecated a bit over time. I very rarely, if ever, use clone, but you can use it, and you can use it to implement a variant of the prototype pattern. So that would be something else to think about as a good example of a known use that's widely popular. So to wrap up, we use prototype together with bridge, as we so often do, combining these patterns because they like to work together in order to ensure the proper semantics of post-increment operations for our STL-based expression tree iterators. As you can see here, the expression tree iterator, which defines the abstraction role in the bridge pattern, uses the clone method on the iterator impl to get the appropriate clone of the corresponding concrete type of whatever iterator strategy has been configured for this particular iterator without exposing those details up to the client code that's written using the bridge pattern as part of the abstraction role.